Hello friends, welcome back to my YouTube channel. In this lecture I am going to discuss a very important topic, that is a steady flow energy equation, which is important in the sense that in each and every year some questions are asked in the GATE exam from this topic. But the problem is there are certain confusions in the minds of students regarding these equations. So I want to eliminate those confusions in this lecture. Before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. Let's get started. So first we must identify what are the confusions that arise in the minds of students about this steady flow energy equation. You see, first confusion relates to the heat transfer and work transfer. You see, heat transfer and work transfer are the modes of energy transfer which is there in case of both closed and open system. In closed systems also there are heat transfer across the system boundary, and there is also some work transfer across the system boundary, and that also happens with the control volume or open system. But why in that equation Q is expressed always with the incoming fluid stream that enters into control volume, and W is usually expressed with the exiting or outgoing fluid stream leaving that control volume. Why this is so? And second confusion relates to the which equation has to be used more conveniently at which situation, because there are two equations, there are two forms of steady flow energy equation. One is in the rate form, that means in that equation each and every term of the equation is expressed with units of kilojoule per second or joule per second, and in the second form of equation is the energy steady flow energy equation per unit mass form, in which the energy unit of every term is in form of kilojoule per kg or joule per kg. So how to select which equation is more convenient for what kind of situations, that we want to know. So first we must understand what is steady flow process. You know, most of the engineering devices like turbine, compressor, all those devices operate under steady flow conditions, and those are basically the open systems or control volume, and they are steady flow devices. What is this? Is suppose this is control volume. You know, control volume is nothing different from the open system, and suppose here is some mass is entering into the control volume and some mass is leaving the control volume. Obviously control volume means there is mass interaction between the system and surrounding. Control volume is same as open system, you see. So this is your control system. So steady flow process means after certain transient periods, every devices like turbine, compressor, nozzle, diffuser, etc. attain a steady state when no property, either extensive or intensive, vary with time. So that's why that is steady. Steady, the literal meaning of steady is invariant with time. So in that process, what happens? Neither intensive nor extensive property vary with time in that case. That means the mass of the control volume and energy of the control volume or volume of this region also do not change. Both mass, energy and volume, none of these value actually change during the steady flow process once that steady state is attained. After some initial transient periods, then steady state is attained by almost all the engineering devices, and under that conditions those devices operate over a long period of time. So this is what the steady significance of steady flow process is. So how to derive steady flow energy equation? Usually steady flow energy equation is derived on the basis of two principles. One is principle of mass balance, and second one is principle of energy balance. What are those two things? You see, mass balance. What is principle of mass balance? Suppose this is the control volume. This is suppose the control volume. This is control surface. This is suppose control volume. Here some mass is entering into control volume and some mass is leaving. Suppose 15 kg mass enters into control volume and 5 kg leaves the control volume. 15 kg enters, 15 kg of fluid enters into control volume and 5 kg leaves the control volume. That means 15 minus 5, 10 kg is accumulated in the control volume. That is called principle of mass balance. Same is with the principle of energy balance. Energy is neither created nor destroyed. It can only be converted from one form to another. So according to energy balance also, this is energy balance, principle of energy balance. You see, suppose this is the control volume. Here suppose 20 kilojoule of energy enters into the control volume. This is control surface. And 15 kilojoule leaves the control volume. The net energy, that is 20 minus 15, is accumulated in the control volume. Every bit of energy is to be accounted for. That is what the energy balance means. So, but what happens in steady state? We know that mass of control volume is equal to constant and energy of control volume is also constant. So neither mass nor energy can be accumulated during any kind of steady flow process. So whatever mass enters into the control volume must leave the control volume to keep the mass of the control volume constant in case of steady flow process. So similarly, whatever energy enters into control volume must leave it so that there is no accumulation of energy within the control volume. That means in case of steady flow process, what is the mass balance equation? So what is the mass balance equation? Suppose this is M in minus M out is equal to mass of fluid entering into the control volume is minus mass of fluid leaving the control volume is equal to delta M, change in mass of control volume. This is the basic principle of mass balance. But for steady state, what happens? This delta mcv is equal to 0. And if you take this equation in rate form, I will write this per second. M dot in minus M dot out is equal to dm of cv divided by dt. So since this is a steady flow process, anything you differentiate with respect to time will be 0 because no property will vary with time. So that means M dot in minus M dot out is equal to 0. This is the mass balance equation for the steady flow process. So whatever mass flow rate enters into control volume per second, so what does this equation represent? M dot in equal to M dot out. So whatever mass enters into the control volume per unit time is equal to the mass leaving the control volume. Similarly also, if you apply the energy balance principle for steady flow system, the result will be like this. E dot in minus E dot out, total energy entering into control volume minus rate of energy entering into control volume minus rate of energy leaving the control volume will be 0. That means E dot in equal to E dot out. From these two equations only, the steady flow energy equation is derived. First one is M dot in equal to M dot out and second one is E dot in is equal to E dot out. So suppose there are multiple inlets in case of a steady flow device. It's not necessary that always there will be there will be single inlet and single outlet. There may be some multiple inlets and multiple outlets also. Of course, this is a different thing that there are certain devices like turbine, compressor, nozzle and diffuser. There are mostly single inlet and single outlet. So we'll derive the expression for multiple inlet and multiple outlet. So you see what are the basically the energy interactions in case of open system. You see the heat is already there. heat q dot is the rate of heat entering. Suppose maybe there may be some heat interactions at the inlet and there may be some other heat interactions at the outlet also. This is possible. It's not necessary that only heat will enter the system and heat will not leave the system. There is nothing like that. So suppose heat may enter into the system. Suppose the rate of heat entering into the control volume is q dot in, and rate of work that is entering into control volume is suppose w dot in, and rate of heat leaving the control volume is q dot out, and suppose rate of work that is leaving the control volume is suppose w dot out. So you see, what are the energy interactions in the open system? Energy interaction in open system or control volume takes place in three forms. In closed system, there can be energy interactions only in the form of heat or work. But in open system, there is always some energy transport by mass also. The mass enters, while the mass enters into control volume, it carries some energy with it. And when the mass leaves the control volume, it also carries some energy with it, carries away some energy with it. So we have to take that into account. So in case of closed system, only heat and work interactions are there. But in case of open system, along with this Q and W, some energy transfer can also take place with the mass either while entering this control volume or during the leaving the control volume. So that we have to take into account. But there is a difference between the W in case of closed system and in case of open system. In closed system there can be boundary work, but in open system there cannot be any boundary work, because since the volume is constant, then PdV work will be 0. In case of steady flow system, there cannot be any boundary work. So only work that is present in case of steady flow system is shaft work and electrical work. Shaft work or electrical work. Shaft work is external work and electrical work is also external work. Only these kind of work can be present in steady flow devices. No boundary work is present in steady flow devices. So that is the basic difference between the W that is used in case of closed system. In case of closed system, the PdV work can be present. And another important thing is there is some flow work which is required for maintaining the continuous flow of fluid into the control volume or out of the control volume. That we have already discussed in flow work. Suppose the pressure of the fluid while entering into a control volume is P and specific volume is B, then this PV represents flow work per unit mass. Pressure multiplied by specific volume. So energy of a flowing fluid, suppose during this entering of the fluid into the control volume, suppose I will say what is the energy that comes into the control volume with this flowing fluid. Energy of a flowing fluid will be theta, is usually expressed in the form of theta, that is this represents energy of flowing fluid per unit mass, and that is H plus V square by 2 plus Gz. You know that for a non-flow fluid, this is the summation of energy, U plus V square by 2 plus Gz, and this PV term comes into picture only in case of a flow process, because this is the flow work. Whenever this flow work is imparted onto a fluid element, that is conserved in the form of energy of flowing fluid. So theta, that is energy of flowing fluid per unit mass, I can write this is H plus V square by 2 plus Gz. So now I will write the energy balance equation. So Q in, if I express the energy balance equation in rate form, that is Q dot in plus W dot in plus, suppose there are multiple inlets, I will write M dot in h plus b square by 2 plus gz. This is for each inlet, each inlet, this is in, equal to q dot out plus w dot out plus sigma m dot out h plus b square by 2 plus gz. This is for each outlet. So in the inlet heat interaction can take place, and in the outlet heat interaction can also take place. In the inlet work interaction can take place, that means work can enter into the control volume, and the outlet also work can go out of the control volume. There is no restriction on this. So I will take each and every term into account, and according to specific conditions I will apply. Suppose in a case there is no heat flow, then both these two terms will be eliminated, and that those terms will be reduced to 0. From this I can write the equation like this: q dot in minus q dot out. These are three terms in the energy associated with this summation is q dot in the heat that enters into the control volume per unit time. W dot in means it includes either shaft work or electrical work. Suppose in case of a steady flow device there is no electrical work, then neither any electrical work nor shaft work, then this term will be eliminated. That depends upon the situation. This is the most generalized form: q dot in minus q dot out. I can write this like this: plus w dot in minus w dot out equal to sigma h plus b square by 2 plus gz minus so this I can write, suppose this is equation, I can write this q dot net input, q dot in minus q dot out, heat input minus heat, that is heat added minus heat rejected, that results in net heat input into the control volume, plus this is I can write minus net heat work output. Since w dot in minus w dot out, I can write like this: minus of w dot out minus w dot in. That means net work output, w dot output. I can write this is equal to sigma m dot out Supposing that there is a single stream, of fluid entering into control volume and single stream of fluid leaving the control volume, then there will be single m dot. So this equation will be, most of the cases like turbine and compressor and nozzle and diffuser, there is single stream of fluid entering and single stream of fluid leaving. Then q dot net heat input. So I will understand this like net heat input, but in most of the books you will find that q dot is written on one side. So what one will understand, but we have to understand that is net heat input. Suppose in the inlet 10 kilojoule of heat is entering into the control volume, and the outlet 5 kilojoule of heat is leaving the control volume. That means the net heat input will be 10 minus 5, that is 5 kilojoule. That is what we have to understand. So q dot net heat input minus w dot is net work output, net work done by the system. Work output means net work done by the system, is equal to m dot. You know, whatever mass flow rate enters into control volume is equal to the mass flow rate leaving the control volume. So I will write single m dot for both these two things when there is a single stream of fluid. M dot h plus b square, I can write for exitant, I can take subscript 2 s2 plus v2 square by 2 plus gz2 minus m dot h1 plus b1 square by 2 plus gz1. So I can write like this: Q dot net input, net heat input, Q dot rate of heat, net heat input into the control volume minus rate of work done by the control volume, net work output is equal to m dot h2 minus h1 plus v2 square minus v1 square by 2 plus g z2 minus z1. So I can write q dot net input minus w dot net output. By writing like this, you will have a clarity of understanding. This is if you multiply this, I can write like this: delta h dot plus delta ke dot m dot when multiplied by change in specific enthalpy, that yields change in total enthalpy, rate of total enthalpy, change in total enthalpy. Its unit will be kilojoule per second, plus, so I can write like this. And if you divide this equation, suppose this is equation 1, and if you divide this whole equation by m dot, I will get this equation. If 1 is divided by m dot, and especially if there is a single stream, I can easily divide by m dot, but in case of multiple streams I cannot do so. So in case of single stream, if you divide by m dot, the equation will be reduced to q dot net input minus w dot output, both will be divided by m dot, will be delta small h, change in specific enthalpy, delta small kinetic energy, change in specific kinetic energy, change in specific potential energy. So I can write q specific, this is q, small q, its unit will be kilojoule per kg, minus w cv I can write. It is usually written as control volume work or shaft work. And if it is if there is some electrical work present, as in the case of water heater, then that has also to be taken into account. Whenever electrons are crossing, suppose this is a control volume, and this is a control volume, and suppose here some electrons are crossing the boundary, then we can say that some electrical work is given into the control volume. So I can write q minus wcv is equal to delta h plus delta ke plus delta potential energy. All these unit of each and every term, that is change in specific enthalpy, and its unit will be kilojoule per kg. Its unit of this term is also kilojoule per kg. This is especially useful. This is expressed in terms of per unit mass, and this is especially useful whenever there is a single stream of fluid entering into control volume and a single stream of fluid leaving it. And when there are multiple streams, this equation will be more useful. And so there should not be any confusion regarding q and w. Q, usually the convention is that whenever heat is added to the system, it is taken positive and work is done by the system, that is positive. And by convention it is assumed that heat is always converted into work. That's why q is always associated with the incoming fluid stream, and w is associated with the outgoing the fluid stream. But this is the most generalized expression, q net heat input. Suppose there is a nozzle which is insulated. In case of nozzle, there will be no control volume work. That means there will be the work output term will be 0. Nozzle, there cannot be any electrical work also, and there cannot be any shaft work. But of course, in case of a turbine, there can be some shaft work. So in case of a nozzle, this equation will be reduced to what? This term will be 0. And if it is especially an adiabatic nozzle, then there will be no heat term also. So then equation will, both these two terms will be reduced to 0, and this will be the steady flow energy equation. So this is the most generalized form, and according to the situations, equations can be derived from it. So that's all.